What if I told you there's a single object in our solar system, just one, that could erase the surface of Earth so completely that before and after would be two different planets? Not a dinosaur killer, not 10 kilometers. I mean something so large that the idea of a crater becomes almost meaningless. Today we're going to do the most reckless experiment you can do safely inside a simulation. We're going to take Ceres, the biggest object in the asteroid belt, and slam it into Earth at 30 kilometers per second. And we're not just watching the explosion, we're watching what happens to Earth's crust, mantle, oceans, atmosphere, rotation, and long-term recovery. Because the real shock isn't the blast. The real shock is what this does to the planet's operating system, its spin, its climate engine, and its stability. So stay with me, because the ending is beautiful and terrifying. Before we start, I want to explain why this isn't just disaster entertainment. This scenario is a shortcut to understanding how planets evolve. Earth looks stable because we live inside a calm chapter of its history. But the early solar system was chaotic, collisions were common, and giant impacts shaped worlds. It's how planets formed. It's how atmospheres can be stripped away or rebuilt. It's how a planet can reset its surface, its chemistry, and even its rotation. So when we run a Ceres impact simulation, we're not just asking, would life survive? We're asking, what does it take to rewrite a planet? And once you see what rewrite looks like, you'll never look at Earth the same way again. Let's meet our projectile, Ceres. Ceres is about 940 kilometers wide, almost 1,000 kilometers. That's not a space rock, that's a small world. It's big enough to be round, shaped by its own gravity. It's the largest object in the asteroid belt, sitting between Mars and Jupiter. Now compare that to the dinosaur impactor. The one linked to the extinction event was around 10 kilometers across. So yes, Ceres is roughly 94 times wider. But here's the trick. People think 94 times wider means 94 times worse. No, width is dramatic, but mass is what destroys planets. And mass scales fast. A 10-kilometer asteroid is a bullet. Ceres is more like a moving mountain range, and it carries thousands of times the mass. So we're not doing another dinosaur event, we're doing something closer to a planetary reboot. 30 kilometers per second, about 108,000 kilometers per hour. At that speed, the impact isn't like hitting a wall, it's like turning matter into energy instantly. In impacts, kinetic energy scales with the square of velocity, so doubling speed quadruples energy. 30 kilometers per second is not just fast, it's catastrophic. At that speed, rock doesn't behave like rock, it behaves like fluid. It vaporizes, it ionizes, it becomes plasma. So when Ceres hits Earth at 30 kilometers per second, it's not a big crater, it's a physics event so violent that Earth itself becomes the stage. In the simulation, the first thing you notice is psychological. Ceres approaches and it stops feeling like an object and starts feeling like a second moon, a cratered, dark disk growing larger every hour. The sky would change. Nights would feel different, brighter, heavier, wrong. And then comes the final moment when you realize there's nothing to stop it. No missile, no deflection, no last-minute plan. At this mass and speed, Earth is about to take the full punch. And then it happens. Impact begins with light. From orbit, you'd see an instant bloom, a white-hot flash so bright it would overwhelm cameras. Then the shock front expands, not like a wave, like a circular pressure wall racing across the planet. The atmosphere becomes a weapon, supersonic winds, instant heating, pressure spikes that crush structures before fire even arrives. And there's a strange detail. The impact is so energetic that the concept of ground zero stops being local because the energy doesn't remain at the surface. Ceres doesn't just hit the crust, it drives through it. Most impacts create craters. This creates an impact basin. Ceres is so huge that it punches through the crust, into the mantle, injecting energy deep into the planet's interior. The crust is thin compared to the scale of this collision. It's like cracking an eggshell with a cannonball. The shell doesn't resist, it fails. The basin can reach thousands of kilometers across. Not a city, not a country, a feature on the scale of an ocean. The energy doesn't stay at the surface, it is injected into the planet's interior. And that matters, because the mantle is Earth's long-term engine. It drives volcanism, it shapes continents over millions of years. So we're not only destroying the surface, we're disturbing the machinery underneath. At this point, it helps to do a comparison. People ask, how many nuclear weapons is this? That comparison fails because every nuclear weapon on Earth combined is tiny compared to the scale of energy. Not smaller, tiny, like comparing a spark to a star. This impact releases energy equivalent to an unimaginable number of dinosaur-killing impacts. And even that doesn't fully capture it, because the dinosaur event was catastrophic for life, but Earth remained a planet with oceans and continents. Here, we are pushing Earth toward a state where ocean becomes steam and continent becomes melt. So nukes aren't relevant. This is not a weapons-level event, it's a planetary physics event. Now for one of the wildest consequences, Earth's rotation. Earth spins, and that spin contains a huge amount of kinetic energy. It's part of what makes the climate stable, because rotation shapes wind patterns, ocean currents, and day-night cycles. A Ceres-class impact can carry enough angular momentum to disturb Earth's rotation. That means Earth's day length could shift, not by milliseconds, potentially by hours. Imagine waking up and the concept of a day has changed. Sunrise timing shifts across the globe. The climate engine reboots around a different rhythm. Rotation also influences the distribution of ocean water and atmospheric circulation, so the impact is not only rewriting the surface, but rewriting how Earth behaves as a rotating system. And the moment you change rotation, you change long-term stability. Now, the debris. The impact launches enormous quantities of material upward. But up is not enough. It launches it out. Molten rock, vaporized crust, superheated dust. Some of this debris reaches escape velocity and leaves Earth forever. But a lot of it doesn't escape. It falls into orbit around Earth. And that's when something eerie happens. Earth forms rings. Rings sound beautiful because Saturn trained our brains to think so, but these are not icy rings. They're rocky rings, hot rings, superheated rock, ash, glassy fragments orbiting the planet, reflecting sunlight, casting shadows across the surface. From space, it's stunning. From the surface, it's the start of a long nightmare, because rings don't stay stable forever. They grind, they collide, they decay, and when they decay, they come back down. But we're not there yet, because Earth still has one more transformation coming: the atmosphere and oceans.
As the shock wave spreads, the atmosphere heats violently. The air becomes dense with ash, dust, vapor, and aerosols. Visibility collapses. The sky darkens, then glows, then darkens again because the planet is wrapped in a thick, chaotic envelope. It's not stormy. It's a temporary new atmosphere built from impact vapor, and the temperature is extreme. The air itself becomes a global heat transfer system, carrying heat around the world, turning the concept of safe regions into a myth. Even if you hide from the shockwave, the heat and atmospheric collapse follow. Now the oceans. The dinosaur impact caused global collapse, but the oceans remained oceans. Here, the energy scale is so large that water rapidly transitions into steam. You don't just get evaporation, you get a phase change crisis. The top layers flash into vapor, then the vapor traps heat like a greenhouse. More water evaporates, more heat is trapped. The planet's surface becomes a feedback loop. Heat creates vapor, vapor traps heat, heat creates more vapor. And when oceans go steam-heavy, weather as we know it ends.
There's no normal rain cycle, no normal clouds, just a superheated envelope over a planet that is beginning to glow. Now the defining image. Earth becomes a global magma ocean, not lots of lava, a planet-scale molten surface. From orbit, Earth would look like a newborn world, glowing orange-red with darker cooling patches like scars forming and breaking. Continents disappear, coastlines lose meaning. The surface is a moving molten layer, and the atmosphere above it is thick and hostile. At this point, we're no longer watching a disaster. We're watching Earth convert into a different planetary state. And now, the long timeline begins. After the initial violence, you get a strange phase. Earth is still active, still hot, still hostile, but the big explosion is over. The planet starts radiating heat into space, slowly, relentlessly. But cooling is not smooth because debris in orbit is still there, and debris in orbit is unstable. This is where the rings become the next chapter. As ring particles collide, they lose energy and drop. Their orbits decay, and then it begins. Ring rain. At first, it's sporadic streaks, bright re-entry trails. Then it becomes continuous, a constant bombardment. Not like a meteor shower you watch once a year, like a permanent feature of the sky. This re-entry adds heat, it adds impacts, it delays cooling, it creates a repeated trauma loop for the surface. Earth is trying to form a crust, and the ring rain keeps tearing it apart. It's like the planet is rebuilding itself while being sandblasted by fire. Eventually, despite the punishment, cooling wins, slowly. A crust begins to form, thin at first, like ice forming over boiling water. It cracks, it shifts, it breaks. Molten rock pushes through seams, but over time the crust thickens, and that's the beginning of land again. Not the old land, a new skin. If you could stand on it, you'd see a dark basalt-like surface broken by glowing fissures, steam vents, ash, a sky still choked with particles, but you'd also see the first sign that Earth can become solid again. What happens to water depends on how much remains and how much was lost to space, but if enough survives, the planet can cool to a point where condensation begins. Steam becomes clouds, clouds become rain. Imagine rain falling on a hot crust. It flashes into vapor, then condenses again, a violent water cycle as the planet tries to find balance. Over long timescales, water can pool, oceans can reform, but they are not our oceans. They are new oceans on new crust with new chemistry. As the planet cools and the atmosphere thins, climate begins again, but it's not smooth. Ash can block sunlight, greenhouse gases can trap heat, the balance can swing. Earth may pass through extreme phases before stabilizing, depending on what gases dominate. And stability isn't just temperature, it's circulation, chemistry, rotation, the ocean-atmosphere engine locking into a sustainable rhythm. After a Ceres-class hit, that engine has been disassembled and rebuilt. Now zoom out in time. Hundreds of thousands to 1,000,000 years later, Earth can look like a planet again. Clouds, oceans, land. But it's not the same Earth. Continents would be different.
The atmosphere could differ. This is Earth after replacement. Same orbit around the Sun, same basic mass and gravity, but a new surface story. And if life ever returns, it returns to a world that is not a continuation, but a restart. Now step back from the simulation and ask the uncomfortable question. Earth is 4.5 billion years old. Human civilization is tiny on that scale. We know giant impacts happened early. We know the solar system was violent. We know planetary surfaces can reset. So how many times has Earth experienced partial resets or massive reorganizations, events that would erase surface evidence? And if that happened, what would survive? Not cities, not roads, but maybe signatures, chemical markers, unusual mineral layers, isotope anomalies. That's why ancient civilizations before us is mostly speculation, but Earth has been reset before is not. The planet has a history of transformation. People ask, would we see Ceres coming? In real life, an object that large is easier to track than a small one, but detection does not equal prevention. Deflection works best with long lead time and smaller masses. For something like Ceres, the mass is so extreme that moving it becomes a monumental engineering problem. In other words, seeing it coming would only change one thing: how long we have to be terrified. This is why universe sandbox-style simulations are so addictive. They let you feel scale. You watch the asteroid approach, and your brain finally understands a planet is not a fortress, it's a target moving through a shooting gallery of space. Earth feels less like the ground and more like a ship with systems, rotation, atmosphere, oceans that can fail. The simulation makes something abstract feel real, and once it feels real, you start to ask better questions about our actual universe. There's also something psychologically weird here. The destruction looks beautiful. Earth with rings is stunning. A glowing magma world looks cinematic. Meteor rain across the horizon is mesmerizing. But it's beauty created by violence, and that contrast is part of what holds attention. Your brain is caught between awe and fear. So what happens if we slam the biggest asteroid in the asteroid belt into Earth? Not a crater, a planetary wound. Not an extinction, a planetary reset. Earth's crust is breached, the mantle is shocked, the oceans turn to steam, the surface becomes magma, debris forms rings, rings fall back down as fire. And after a very long time, Earth rebuilds, but it's not our Earth anymore. So here's the final question. If one impact can erase a planet's surface and rewrite its rotation, how fragile is the world we call normal?